Okay, we're ready to go. So I'll hope to be able to get the WebAssign arranged. I hope today. There is one. There are a few announcements, and some of them don't really pertain to you, except just my presence on campus type thing. Next Tuesday, I have a doctor's appointment at 10 o'clock, but I have to be there for labs at 9 o'clock, so I won't be on campus that morning, because if I came to campus, I'd have to leave by 8:15 to go back to the clinic. So I'm not going to be here until after the appointment's over. I'm hoping that will be 11 o'clock. But normally I'm in classes that time anyway. It's just those classes I'm having to make up. So it doesn't really affect office hours in. Number two, seemed like there were two things. I can't remember what the second was, but the third one is, I don't know if any of you know Miss Nyla Geraci on the Birmingham campus, but she is recruiting students who want to be on the math team. And I know that some of the math that they'll be doing on that is a little beyond probably what you have now, but it's still a pretty good experience. So if you want to come and participate in that, she would love to have you. So you can either tell me, we'll have some practices here on this campus Monday, Wednesday, and this is a little bit of a problem. My only office hours on this campus are Monday, Wednesday, 3:15 to 5:15, and I have some students who want to have practice Monday, Wednesday, 3:15 to 4:45. So there goes part of my office hours. Now, we may not be every Monday and Wednesday, but it really shoots into office hours, but we'll manage somehow. So anyway, if you are interested, either let me know, and I'll get the information to her, or you can contact her directly if you'd like. Her email is ngeraci, that's J-A-R-A-Y-S-I. I'll write it down for you if you want, at lawsonstate.edu. So if anyone's interested, please let me know, and we'll say, and if you want to come by one of the practice sessions on Monday or Wednesday afternoon, 3:15, I assume we'll start today, but I don't know if the student's going to be there or not. The only one who's expressed interest so far. I've got my Cal 2, Cal 3, and differential equations class later today, so I'm hoping to pick up some more students. Okay, Tara is here. Anyone else come in since the call roll? Okay. Seems like there was another announcement, but I don't remember what it is now. So, all right. We had done, this is not example 9 in our book. I had my paper in the wrong place, so I don't know exactly where we left off. Did we finish 3-4, or did we have some yet to go? I have a couple of marks here, but I've taught from this book before, so I don't know if they're current marks or previous marks. Seems like we did the area of a square. We were working on the right circular cylinder, or did we finish that? What's that? We did finish, okay. I had a mark there. So evidently we finished 3.4. I had my paper one page too soon. I thought it was one page too late. Sorry about that. Let's back up and go to 3.5. All right. Any questions on 3.4? A pretty quick review, maybe not quick enough, of basic factoring. Now we'll do a few other kinds of factoring if I can ever get the PowerPoint open. Go through all this again. So any questions while we're waiting? Okay. This is like watching paint dry. Okay. All right, we'll get the slideshow set up from current slide. There you go. And again, we're continuing with polynomials. This section, 3.5, is another two ways of factoring. And these specific ones that we're focused on here, difference of two perfect squares and the sum or difference of two perfect cubes. And your name, please? Donna, I thought so. Okay. All right. Anyone else come in since the call roll? All right. So our objectives in this section: factor the difference of two perfect squares, factor the sum or the difference of two perfect cubes, use factoring to solve equations, and solve some word problems that involve factoring. These last two we do in just about every one of them. Okay? So let's look. Do you remember, this is a little bit of review, and if it's unnecessary review, let me know. Give me a letter, any old letter. 4? A, okay. I was going to say 4 is not, okay. A, plus or minus? Plus. Any other letter or number, I don't care. Second? B, okay. Now, I want to multiply that by A minus B. This is called the sum times the difference of the same two numbers. Anyone remember what that yields? Just looking at it? Second? Okay, let's FOIL it and see what we get. Now, you were here before, right? Yeah, okay. So we'll do the first, and what does that give us? A squared. Then outer minus AB inner plus AB, and then finally last minus B squared. And what do you notice? What do we do next? Combine like terms. And what like terms do you see? Yeah, plus AB and minus AB. When you combine them, what do you get? Absolutely nothing, okay? They add to 0. So what do you get? A squared minus B squared. Anytime you multiply the sum times the difference of the same two entities, whatever they are, they can have numbers in them, they can have letters in them, they can have expressions in them. If you're multiplying the sum times the difference of the same two entities, you'll get the difference of their squares. Guess what? Because of that, reverse it. Anytime you have a difference of two perfect squares, guess what? You can factor that as the sum times the difference of their square roots. There it is. I mean, it's just pretty simple. Going back, that's why the smiley face is smiling. It's that simple. Okay, and this is reiterating that A plus B times A minus B is A squared minus B squared. Same pattern, do it in reverse anytime you have a difference of two perfect squares. And again, the A can be a number, a letter, a combination of letters and numbers, an expression. It could be a binomial, anything squared minus anything else squared. You'll get the first thing plus the second thing times the first thing minus the second thing. Not the square of the square root of those. Applying the pattern is fairly simple, and we'll do the example. So let's do some of these. What would be the A here? Let's do that right here. Do we have room? What would that be? How would that begin? Now, we could unfoil it if you want to go that way. Okay, X, say again. I can't hear. Okay, X plus, okay, is it 8? 4. 4. The square root of 16 is 4. Half of 16 is 8. Square root times X minus 4. Very good. How about number B? A little more involved there, but not bad. What would that be? 2x plus 5 times 2x minus 5. Boy, how about this one? 4x minus 3y, 4x plus 3y. Doesn't matter what order you put the plus or minus as long as you get one of each, right? And how about that last one? Is that doable? Is it? 1. Good. Minus a times. Got it. Yeah, there they are. Let's see how they did it. Okay, the first one they noted was the difference of x squared and 4 squared. That's how they started. I don't see that as a necessary step, but if it helps you, do it. Okay? And then that would be the sum times the difference of those square roots. X plus 4 times x minus 4. Just like you did. Okay? The B, they noted that 4x squared was the perfect square of 2x. 25 is the perfect square of 5. Difference of two perfect squares, it would be the sum of these two numbers times the difference of those two numbers. In whichever order you want to do them, 2x plus 5 times 2x minus 5. Just like y'all got it. Okay? Going to go to a new screen so you lose what you see, but remember it. 16x squared, again, this step to me is unnecessary, but if it helps you, do it. 4x squared minus 3y squared. So that'll be 4x plus 3y times 4x minus 3y. And that's exactly what they get. And then finally, 1 minus a squared. Remember your perfect squares. 1 is a perfect square of 1. So that's 1 squared minus a squared. So that'll be 1 plus a times 1 minus a, or whichever order you want to do it. Does that make sense? Pretty straightforward, hopefully fairly simple. Any questions? Any doubts about it? Okay? Now, that was example 1. They continue. Multiplication is commutative, so the order of writing those doesn't matter. We've already said that. If you write that as x minus 4 times x plus 4, x plus 4 times x minus 4, multiplication, it doesn't matter what order you do. You must be careful not to assume an analogous factoring for the sum of two perfect squares. There is no factorization for that. There's no two expressions you can get that you multiply them together will give you x squared plus 4, for instance. None, ever. Well, you have to get into the complex number system, okay? You can't do it in the real number system. If you're thinking that's going to be x plus 2 times x plus 2, think again. Foil this. X times x, x squared. X times 2 is 2x plus 2x, 4x. This doesn't have a 4x in it. The plus 4 works, the x squared works, but you can't account for the plus 4x. So no, there is no factorization for the sum of two perfect squares. Ever. Don't even try. We say that a polynomial such as this that cannot be factored, just like a number that cannot be factored any more than itself times 1 is a prime number. We call this a prime polynomial. It is not factorable using integers. In fact, you can say it more strongly, not factored using real numbers even. Okay? We're sticking with integers now. Sometimes the difference of two squared pattern can be applied more than once. Okay? In other words, when you're factoring, always stop and ask yourself, can we factor any further? Okay? And many times you can, sometimes you can't. They skipped the next two examples, example 2 and 3, so let's back off and do them here. Okay? Okay. Example 2. X to the 4th minus y to the 4th. Is that factorable? What you think? Yes? How would we factor it? x squared plus y squared, x squared minus y squared. Very good. Are we through? No, we're not. Can we factor this one any further? That's the sum of two perfect squared. You can never factor a sum of two perfect squares. Ever. But, how about that? Yes or no? Yay or nay? Yay, yeah, you can cheer. Okay, yeah. Will that factor? I'm going to write this one down. X squared plus y squared. That's prime. Okay. How about this one? Will it factor further? Will it? X minus y times x plus y. And those won't factor any further. There, you got it. Factored completely. Okay? How about this one? 16 x to the fourth minus 81 y to the fourth. Now, it may be in these kind of problems, you might find their method of writing something squared minus something squared may help you see it. Possibly. If not, you can do it without doing that step. But remember, that step is there for you if you need it. What would you do with that one? Is it factorable? How? 4 x squared minus, say again, 9y squared for x squared plus 9y squared. Very good. Are we through? Why not? That first one will factor further. How will it factor? 2x minus 3y, 2x plus 3y. How about the second one? No, it will not factor. You cannot ever factor the sum of two perfect squares. 4x squared plus 9y squared. Now you've completely factored both of those. Make sense? Okay, if you're checking the book, you'll see they also got these answers. First one, x squared plus y squared times x plus y times x minus y. Whichever order, it doesn't matter. The second one, again, the order is different, but 4x squared plus 9y squared plus times 2x plus 3y times 2x minus 3y. Very good. All right. Any question? Now, by the way, I can't remember if the previous edition had these, but this edition has on the sort of inside margin the classroom example. I wish we had time to do this, but we just don't have time enough to do it. We're doing it with these, so take these home. You don't even take them home. First chance you get outside of class, try to work these examples. While it's fresh on your mind how we did it, then try to work those classroom examples. Okay? You have them in your text too, right? Do you? Okay. Do y'all have answers given? I guess not, but do you? On the classroom examples? I have in a little blueprint the answers. Do y'all have that on those classroom examples in the inside margin? Or you just have the problems? Just the problems? Okay. I'm guessing your answers are somewhere. They may be on the back of the book or at the end of the section or somewhere, but mine has them there, but I have the instructor edition, so I never know exactly what yours looks like. We're on page 153. You don't have the answers given there. I bet you they show up somewhere, I just don't know where. Okay. All right. If you have any questions about them, bring them to class and we'll work them. If you're not sure you got the right answer. Okay. Let's move on to example 3. Whoops. x plus 3 squared minus y squared. Can you do something like that? Yeah, sure you can. How would that factor? Second, x plus 3, bought it, plus y times x plus 3 minus y. You got it. Very good. How about this one? 4x squared minus 2y plus 1 squared. Will that factor? Okay. This one, warning. Be careful with this. How would you begin it? 2x plus, say again, 2y plus 1. That's fine. What's the second factor? 2x. Okay, minus. Here's the warning. Be sure you put that second one in parentheses. 2y plus 1. Why? Well, we could have put this one in parentheses, right? But that wouldn't change anything. A plus in front of parentheses, you just remove parentheses. But you're minus the square root of this thing, which is that. Now, if you left off the parentheses and put minus 2y plus 1, wrong answer. Because when you distribute the minus across the parentheses, what does that give you? I'm going to write down the first one, which is fine. 2x plus 2y plus 1 times 2x minus 2y minus 1. You're absolutely right. Okay? Remember, anytime you have an entity that you're subtracting, put it in parentheses the first time and then distribute. If you start doing too many steps in your head, you're going to probably miss one sometime. So write out as much as you need to. If you can see that without writing it, do it. But I almost guarantee you, optically, you'll just skip over it sometime. So not a bad idea to put that in parentheses. You can put this one too. It doesn't hurt. But then all you do is remove the parentheses, take them off, because the plus doesn't change anything. The minus does. All right, good deal. How about this one? X minus 1 squared minus x plus 4 squared. Is that factorable? What you think? What would it factor as? Say one more time, a little louder. X minus 1 plus x plus 4 times x minus 1 minus parentheses x plus 4. Close parentheses. Now, you could have put parentheses around every one of those, x minus 1 to x plus 4, every time. You would then just remove the parentheses, except for the last one when you have to distribute. So what does this first one give you if you combine like terms? 2x plus 3 times, and you may have to do two steps here, x minus 1 minus x minus 4. And so this will be 2x plus 3 times what? Say again? Negative 5. The x minus x adds to 0. That gives you a minus 5. Now it said factor them, so that's factored. Okay? actually, you could go back in and multiply through, but since you're factoring, why do that? So that's exactly what they got on theirs. And on the previous, we had 2x plus 2y plus 1 times 2x minus 2y minus 1. And the one before that was x plus 3 plus y times x plus 3 minus y. Very good. Any questions on those? Okay. Any entity you have squared, if you got a difference of those two squares, is the sum times the difference of those entities. Okay. And put them in parentheses, especially when following the minus sign. You can put them in parentheses at the beginning or with plus signs, but all you're going to do is remove the parentheses. The minus sign, though, you have to distribute the minus sign across. And always carry it through, and don't stop here, even though that was a thing. Combine like terms. Wow, that came out far simpler than I would have guessed. Okay. Any questions? Everybody got that? So a few people still writing. You got it? Everybody? Okay. Then I'll move on. Okay? All right. It's possible to apply both the technique of factoring out a common monomial factor and the pattern of difference of two perfect squares to the same problem. Here's the key, folks. In general, it's best always to look for the common monomial factor first. Otherwise, you may not even see you've got a difference of two perfect squares. In fact, that's a general rule everywhere. Always factor out any common factors beginning and then see what you can do with what's left. So here are a few of these. How would you begin that? What would you factor? 7, and what would that leave us? X squared plus 4. Can you factor any further? Say again? Yay or nay? Yes? How? No! It's a sum of two perfect squares, not a difference. Okay, how about this one? Can you factor anything? What? 2 xy. So you factor out a 2xy, and what do you have left? 2x minus 7y. Can you factor that any further? No. That's all you got. Just factor out common monomials. Okay? How about this one? X plus 2 times? X minus 2. Nothing special there. There was no common thing. They should have put one in there, but they didn't. They left those for you to do on the examples, right? So let's do... Oh, there's more of these. Okay. How about that? Yeah, factor out a 2, and what do you have left? 9 minus x squared. Are you through? Say again? Why not? You can factor 9 minus x squared again. Leave the 2, don't forget it. And how does 9 minus x squared factor? 3 plus x times 3 minus x. You got it. How about this one? Y squared minus plus 9. No, you cannot factor the sum of two perfect squares. How about this one? No, there's no common factor. How about this one? Wow. X squared plus 4 times x squared minus 4. Are you through? Why not? X squared minus 4 goes again, but x squared plus 4 doesn't, so leave the x squared plus 4. How does x squared minus 4 factor? X plus 2 times x minus 2. Very good. Everybody see that? All right, good deal. You were reading my hands, weren't you? I could tell. Okay, never mind. Okay. All right. Well, they skipped example 4 too. Shame on them. So let's go back and do example 4. Well, all right. Example 4. 2x squared minus 50. Can you factor that? Anybody? Say again? Okay. I heard part of it. Factor out a 2, and what does that leave us with? X squared minus 25. Now we're through, right? Why not? That factors again. 2, don't forget your 2. It's a factor. X plus 5 times x minus 5. Very good. Y'all are great. Okay, how about this one? 9x squared minus 36. Does that factor? How? A little louder? Say again? Factor out a 9. Excellent. What's left? X squared minus 4. Are you through? What do you have? 9 times x minus 2 times x plus 2. Again, it doesn't matter what order you do that. Now, I was a little surprised somebody didn't say, that's a difference of two perfect squares, isn't it? That would be 3x plus 6 times 3x minus 6. Did you stop there? No, because each of those factors has a common factor of 3. Here you took care of that first. So it's always a good idea to get the common factor out first. That leaves you a simpler factorization at the end. And you make sure you get them all out. Okay? So that is the better way to go. You can go the other way, but it will sometimes lead you to difficulties. And we like to avoid difficulties, don't we? Okay. No, we love difficulties. Okay. 48 y cubed. Wait, we can't do anything with y cubed, can we? Minus 27y. Does that factor? Yes. How? Say again? Okay, I see a 3y. What's left? 16 y squared minus 9 minus 9. Are we through? Why not? Because that second factor is the difference of two perfect squares. What would that be? Second, 4y plus 3 times 4y minus 3. Got it. Okay. On first glance, that didn't look like it could possibly be a difference of two perfect squares. You had a difference, we'd have a cube and stuff. Factor out the common factors, then see what you got. Sure enough, one came out of the woodwork, didn't it? All right, let's make sure they got them right. It looks like they did. Good deal. And again, there's classroom examples in the inside margin. Do those. Okay. Now, let's see if we can pick back up with the PowerPoints. All right. I think we did the rest of those. So now we're ready for factoring the sum and the difference of two perfect cubes. All right. We're going to start again, before we get there, with, you give me a letter or a number. X plus or minus? Plus. Something else. Y. Why not? Okay. Now I'll give you a second factor. Okay. X squared minus xy plus y squared. Okay. Now I want you to multiply that. Now this isn't exactly a FOIL because it's got too many terms in it, but you use the same principle. Okay. Let's start with the first. What does that give you? x cubed. Very good. Okay? Then do the first and the second. What does that give you? Minus x squared y. Very good. Now do the first times the third. Plus xy squared. Okay? Now do the second with the first. Plus x squared y. Is that what you said? Yx squared. Okay, but it's commutative, so that's the same thing, right? Okay. Now the second times the second. And what does that give you? Minus, what's that? xy squared. And now the second times the third. Plus y cubed. Let's add those together. X cubed, 0, 0, plus y cubed. Hey, here we have a sum of two perfect cubes, a sum. And yet it has a factorization. X plus y times x squared minus xy plus y squared. Okay? Now, in just a minute, I'll give you a simple way to think of that. Or at least to me it's simpler. I hope it will be for you. But let's go back and change something. In fact, let's change two somethings. X minus y times x squared plus xy plus y squared. And let's do the same thing again. First times first is, say again, x cubed. First times second is plus x squared y. Is that what you said? Okay. First times the third plus xy squared. Second times the first. A little louder. Negative x squared y. Okay, yx squared, same thing. Next, negative x y squared. And the last, negative y cubed. And when you combine like terms, you get x cubed, 0, 0, minus y cubed. So, for cubes, perfect cubes, both the sum and the difference of the perfect cubes will factor. Every time. You have the sum or difference, two perfect cubes will factor. How about squares? Difference only. Sum of two perfect squares will never factor. Okay? So, as we pointed out before, there exists no sum of squares pattern analogous to the difference of squares factor pattern. That is, a polynomial such as x squared plus 9 not factorable using integers or even real numbers. However, the patterns do exist for both the sum and the difference of two perfect cubes. These patterns are as follows. Okay? Now here's how I do it. I don't memorize well, so I create little patterns for myself. So you got the sum of two perfect cubes. The first factor is always the cube root of this one, same sign, cube root of that one, a plus b. Okay? Now, open parentheses, forget about this part. Okay? Now get your name, please.
It's JT. JT. JT.
JT, you got it. Okay. My hearing's bad, but okay, good deal. Anyone else come in since the call roll? All right. So here's the pattern. Do the cube root of this, same sign, cube root of that, a plus b. Now, forget about this. Square the first. Opposite sign, the product of the two. Not twice the product of the two. And then square the last. Okay? That's what you do. On this one, same rule. Cube root, same sign, cube root. A minus b. Forget this. Square this one. Opposite product. Product here would be minus ab. Opposite of that is plus ab. And then do a plus. The square of the second minus b times minus b is plus b squared. It'll give it to you every time. Okay? And that's what it is. Therefore, when you gave me whatever you gave me, I use that little rule to get the second pattern, second factor. And guess what, folks? Once you do this, don't ever try to factor that any further. It won't. Ever. Okay. Later we'll be factoring trinomials. That's a trinomial. You will not be able to factor those any further. So when you have a sum or difference of two perfect cubes, you have a binomial times a trinomial. Binomial, it'll be simple. Trinomial, even though it looks like maybe you can factor further, hang it up. You can't. Okay. Good deal. All right. So those are the rules. Let's try them. What would be the factorization of this first one? I'm going to do it up here. What would you guess the A would be? Second? Be a binomial factor and a trinomial factor. What will be the binomial? X plus 3. Perfect. All right, maybe a little timeout here. Okay? I'm going to go back a few slides. I'll come back to this in just a minute. Oh, that's a good place to do it. I'm going to clear this out of the way. I don't know how you are in your squares and cubes. If you don't recognize these, here's a good thing to do. And you can do this anytime. Okay? Write down the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, even 10. Whoops, I'm running out of room. Okay? Let's square that. So this is the number. Let's call it n. Now let's do n squared. You can't see the square, but it is up there. What's 0 squared? 0. 1 squared. 2 squared. 4. 3 squared. You know these. 4 squared. Second? 16. 5 squared. 25. 6 squared. 36. 7 squared. 49. 8 squared. 64. 9 squared. 81. 10 squared. 100. Okay. Now, perfect cubes. This will be, I'm going to write it up here, n cubed. Okay? What you do is multiply n times n squared. 0 times 0 is? That was easy. 1 times 1? 1. 2 times 4? 3 times 9? 27. 4 times 16? 64. 5 times 25? 125. 6 times 36? You know, I'm beginning not to care anymore. Okay. It's 216, isn't it? Is that right? See, I'm beginning to lose interest. They're such big numbers. Okay. You won't need to recognize those. But you can work them out. You can take it to 15 or 20 and do the same thing. If you need to recognize those, it's a pretty easy way to get to see your perfect cubes and your perfect squares. Remind yourself of those. Okay? So, you can do that anytime you want to. Okay? On the test, wherever. All right, let's go back to what we were doing. Oops. Okay. So you see 27 is a perfect cube of 3 from that table you just did. So there's the first part, x plus 3. What's the second part, the trinomial part? Square the first, x squared. What sign? Minus. And then the product of those two, 3x. And then plus 9. Perfect, you did it. Okay? How about the b part? You have a binomial times a trinomial. 2a. 2 a. 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 plus 5b. Got it. Now the next part, once you get that, it's fairly easy. What is it? 4a squared minus, say again, 10ab plus 25b squared. Look at you, y'all are good. Everybody see that? Notice where they pulled those numbers from? If you don't ask, we'll go over them again. Okay? How about C? That's yes in Spanish, okay? What would that be? Binomial times a trinomial. What will be your binomial? X minus 1. Very good. What will be your trinomial? X squared, square the first, plus, what? You may have said it, I just don't hear well. Say again? 1 what? X. You can leave off the 1 if you want to. Plus X. Plus 1. Got it. Very good. Everybody see that? What you do, square the first, opposite the product, so that will be it's a minus here, so plus there, product of these two numbers, 1 times x is x. And then plus 1, square the last one. Okay? Notice that last one's always plus. Okay? How about this one? Binomial times trinomial. Three, what you say? Y plus, where'd you get plus? Oh, same sign. Minus. Second. 4. A little louder. X, okay, very good. There's your binomial. How about the trinomial? 9y squared, very good, plus 12xy plus 16x squared. Perfect. Way to go. It's not that bad, is it? Almost fun. Just don't tell anyone else that math is fun. You'll get it. Okay. Want to see how they did it? I bet you they throw in a few more steps. If you find these steps helpful, by all means use them. Okay? So, what they do first is they saw the x cubed plus 27. They wrote that as the cube of x plus, same sign, the cube of 3. Okay? Then to get the first term, they take those two with the same sign, and that will be, first factor would be x plus 3. And then the next factor, here's my little rule, square the first, opposite the product, square the second. You got it. Make sense? Any questions? Okay, let's look at the B. 8a cubed plus 125b cubed. If you find it helpful, take this step and say, 8 is the cube root. The cube root of 8 is 2. The cube root of a cubed is a. Plus, same sign. The cube root of 125 is 5. The cube root of b cubed is b. So, 2a cubed plus 5b cubed. And then the rest is pretty easy. This will just be 2a plus 5b. That should be your first term. Okay? And once you get the first term down there, square the first, 4a squared. Opposite the product. This was a plus, so it'll be a minus 10ab, and then square the last, plus 25b squared. See it? Pretty easy method to do it. Let's go to the C1. And C1 again is x cubed minus 1 cubed. So that'll be an x minus 1. There's your first term. And then it's almost too easy. Square the first, x squared. Opposite the product, plus x. Square the last, plus 1. It's done. Okay? And then the fourth one, D1. The 27 is the perfect cube of 3. Y cubed is the perfect cube of y. So it's 3y cubed minus 4x cubed. This will be 3y minus 4x. Once you get that first term down, the second term is fairly easy. Square the first, 9y squared. Opposite the product, plus 12xy, plus the last one squared. Any questions? You see how that works? Any? Make sense? All right. All right, that was example 5. Okay? Now we're ready to solve some equations. We've been wanting this, haven't we? Okay? Remember that each time we pick up a new factoring technique, we also develop more power for solving equations. Let's consider how we can use the difference of two perfect squares or the sum and difference of two perfect cubes factoring pattern to solve certain types of equations. Here's one. Solve x squared is equal to 16. What would you say the solution was? Second? Look at you. Y'all are so good. I would first write this, and I think that's what you did, as x squared. Well, okay, wait a minute. Subtract 16 from both sides. And that will give you x squared minus 16 is equal to 0. Now, why did I do that? Because anytime you have a high order power, squares, cubed, fourth, 17th, whatever, high order power, get everything on one side, 0 on the other side. Because then, if you can factor, you can use the zero product principle. Okay? So, this will be, as you just jumped right to it, x plus 4 times x minus 4, and that's equal to 0. And what does that lead you to believe? Either x plus 4 equals 0, or x minus 4 equals 0. If you got two things that multiply to be 0, one of those has to be 0, right? There's no way around it. Okay? And what does the first one give you? X equals negative 4. You subtract 4 from both sides. Or x equals positive 4. You can add 4 to both sides. You don't have to. You can just see that's your answer. But that's fine. So your answer, you have two answers, x equals plus 4, x equals minus 4. Now, most classes I've taught before, y'all are much sharper than most classes. Someone in the class would have said, oh, you just take the square root of both sides of that first equation. And what would that have given you? Okay. Say again. Take the square root of x squared, you get x equal 4. Guess what? You got half the answers. You missed half of them because anytime you take the square root of both sides, you need to do a plus or minus. We got the plus or minus this way by factoring, whereas most of the time you'll miss it if you don't stop and think about it. So you would have got half the answer right. That is a right answer, but it's not the complete right answer. It's plus or minus 4. That's what we got in the other. Make sense? Okay. Always a good idea to factor. Okay? Now, they like to write it as a solution set. You can do that if you want to. Okay? And, of course, every one of these, they have a classroom example as well. Okay? Let's see. I think I probably need to erase that. Can I erase it now, or are y'all still writing? Okay? Then they wrote down x squared equals 16. Good thing to write it down again. Okay? Then subtract 16 from both sides. That's what I suggest you do. Then factor the left-hand side. X plus 4 times x minus 4 equals 0. That says x plus 4 is equal to 0, or x minus 4 is equal to 0. This gives you x equal negative 4, or x equal positive 4. So your solution set is minus 4 and plus 4. Okay. Good deal. If you just give me this and I can see it easily, I'm happy with that. Yes, sir. Oh, yes, ma'am. Let me pause this just for a moment. Is my projector working? It doesn't sound good, does it? Has it always been making that noise? That's good. Okay. Okay, what we used before, as we've used in the past, in example 6, one we just did, we use a property that if a product of two entities is equal to 0, it's true if and only if one or the other of those is equal to 0. You can't do it any other way. That property can be extended to any number of factors whose product is 0. So if you have a whole bunch of factors, 3, 4, 17 factors, then let's do it for 3. If the product of A, some entity A times some entity B times some other entity C is equal to 0, that's true if and only if A is equal to 0, or B is equal to 0, or C is equal to 0. And if you had 17 of them, you'd have 17 of those equal to 0. Okay? That would be. And only one of them has to be 0, but at least one of them does have to be. Okay? Now, that was example 6. They're skipping example 7, so let's go back and do example 7. Sorry about that, we had that delay here. How about this one? 9x squared is equal to 64. How would you do that? The square did not write. There it did. Okay? How would you solve that? Say again? Subtract 64 from both sides. Excellent idea. And what does that give us? 9x squared minus 64 is equal to 0. Now what would we do? Where do we look to factor first? Always look for common factors. Unfortunately, there aren't any common factors between 9 and 64. 9 is 3 times 3. 64 is 2 times 2 times 2 times 2 times 2 times 2, you know, a bunch of 2's, and that's all. Okay? No 3's in there. So, we just have to, what do we try next? Say again? No common factors. So can we factor it? Ah, very good. 3x plus 8 times 3x minus 8. Basically, if you don't have any common factors and you have a binomial, just about the only thing you can do is difference of two perfect squares or sum or difference of two perfect cubes. That's all we got for those. And this is a difference of two perfect squares. And that difference equal to 0. And what do we do with that? Either 3x plus 8 is equal to 0, or 3x minus 8 is equal to 0. And what does the first give us? What do we do with that? Subtract 8 from both sides, and that gives us 3x is equal to negative 8. Divide by 3, and that gives us x equal negative 8/3. Okay? Over here we would add 8 to both sides, and that gives us 3x is equal to 8. Divide by 3, That gives us x equal positive 8/3. So you can write the answer as that is perfectly fine, or x equal plus or minus 8/3. Now, is it okay to have fractional answers? Sure it is. They're real numbers. We love our fractions, don't we? Yes, okay? So, perfectly fine. A little bit harder to check that, but you could check it if you wanted to, okay? Actually, it's not too bad. If you square minus 8/3, you get positive 64/9. The 9 cancel out, you get 64. Same thing with that. Now, the other way, if you all had chosen to do it, taking square roots of both sides, that would be 3x is equal to, whenever you do that, you have to remember to do plus or minus 8. And then divide by 3, and you still get plus or minus 8/3. So it will work. You just can't forget the minus. Okay. Unfortunately, that ran us out of time. Sorry about that. We were on track to keep going today. We'll begin next time with example 8. Okay, which means I'd better erase this. Okay? Now, where am I? Here we go. 100. All right. Homework exercises here. On 3.5, do any of the odds 1 through 25? Any of the odds 27 through 49? Any of the odds 51 through 67? And you can start doing some of the odds 69 through 81. If you can't get them all done, hold off. We'll do a few more examples of those later. Okay? That was page 157. Okay? All right. Any questions? Only time I've seen you, yeah. Second. Repeat that again. Okay. Any of the odds 1 through 25. You don't have to do them all, but do some of those. Some of the early ones, some of the later ones. Any of the odds 27 through 49. Any of the odds 51 to 67. And you can start doing some of the odds from 69 to 81. I know you can do some of them. You might be able to do them all, but do some of those. We'll do some more like those next time. Okay? Good deal. It seems strange to see you only one time to say have a good weekend, but that's what's coming up now. This time it's only a 2-day weekend, so enjoy it. And doing math will make it go so much better, right? Good deal. Yes, ma'am.
The research paper.
Right.
Do you want us to put our name at the top of the class and all that?
Whatever you want to do.
Or just,
Whatever format you want. I need your name on it somewhere. Okay.
as long as I have, so I can like, put it at the bottom?
Anywhere you want to, just as long as I can tell it's yours.
Okay.
Yeah.
Okay. Okay.
Some people like to use those headers and stuff, and that's
But
fine with me.
I thought that what you said it wasn't necessary that we use the header.
Not necessary, just anyway, just as long as your name's somewhere on it. So
Okay. Cool. Okay. Thank you.
I'm more interested in the paper itself.
Okay.
And who you are, of course.
Okay.
Okay.
Well, I got mine, so I'll turn this tomorrow.
Fantastic, thank you. I'm sorry.
You know our first question.
When we finish 3.6. It's probably, I hope so.
Do you have that, this, weekend?
What's that?
Do you think you have it this
I'm hoping so.
I hope so.
Yeah, I'm going to try to work on it this afternoon. While Dr. Thomas is available, and make sure that I know all the stuff I need to do on it. Okay. All right. I can't hear you. Say this again. Oh, for Math 100? Okay. Any of the odds on
No,
page...
I'm asking, is this the first assignment?
What's that now?
Is this the first math assignment?
No. Every section we have, those. You can hear them on when you listen to the YouTube.
Okay.
Yeah.
I don't have a book, so.
Oh, I see. You want to take a picture? Only trouble with mine, it's got the answers on them, but we're welcome to it. Okay. You need more light, or is that okay?
That should be okay.
shutting this down while you're doing that.